Thank you for the kind introduction, and thank you for showing up in whatever time zone you are in, whether it's good morning, good afternoon, or good evening. That's our way of life these days, I suppose. So I'm going to be talking about streaming graph processing and streaming graph analytics, and my objective is both to highlight what we mean by those, and to talk a little bit about what we're doing with my students, and that is a segue to talking about the open problems. So one of the important issues to talk about is why this question typically comes up, and I think right now the graph database market is not huge. It's about 781 million US dollars. But the expectation by one market research company, Verified Market Research, says that it will be about 4.13 billion US dollars by 2026. And in trade press, there are all kinds of articles on it. Another one, Markets and Markets, basically says it'll be 2.4 billion by 2023. Gartner says that it's going to be growing about 100% annual growth through 2022, and the cumulative annual growth rate, everybody agrees, is going to be over 20%. So this is serious growth rate, and the graph databases and the graph market is growing. And at one point, I don't know if it is still true, it was the fastest growing NoSQL segment of that marketplace. So the reason these are this is really, the interest is growing, is because when you're paying attention to the relationships and not only the entities, and you want to represent relationships as first-class objects, graphs are the natural data models to use. So a couple of examples from something that's quite in our minds these days, the COVID. The people have used graphs to study multiple things. One study looks at how people interact and influence each other. So the vertices in this graph on the right are really people, and the connections are the edges, and you're basically looking at how ideas and behaviors travel along social pathways. Another study, and this is in China, looks at for people to basically enter either information about your flight or train or whatever you've taken, and then it will tell you, the graph will reach to the known cases, so you can actually check whether you have a chance of being infected. Another study looks at the pathways in social networks. So how does the COVID propagates in social networks using different models, and of course, people have looked at contact tracing. That this is probably the natural application for graphs, and this topic is becoming very current now. And people have also started developing a knowledge graph to be able to collect all the information about COVID, and figure out various facts and reason about the COVID thing. So these are some of the studies that are currently going on, which are on topics that are very much on our minds these days. But modern graphs are very different from each other and very diverse. I'll talk a little bit towards the end on graph analytics, but each of these graphs that we study have different structures, different characteristics, and more importantly, with degree distribution, et cetera, et cetera. So it's really important to be studying these and looking at these. For today's talk, one that I will specifically focus on is a different type of graph. But before I get there, let me just highlight a study that we did and that we published in 2 papers. And this is really Semi and his students are the lead authors on this, and they carried it up. This is a wide survey, including long interviews with users of graphs. And the objective really was we were trying to determine what kind of graph data they use, what kind of computations they do on it, what kind of software they use, what are their stress points. This is from actual users. And then we did a study of 5 years of publications in the database field, conferences and journals in data management, looking at what we study and trying to see if we're really studying the problems that the users care about. And this also revealed that graphs are everywhere in unexpected places. What you would actually think of OLTP type of applications still use graphs. They're very large. Machine learning techniques and using graphs for machine learning is really quite popular. And the scalability is the most pressing problem, and closely followed by visualization and query languages. And for many of these systems, because the graph processing platforms and graph database systems do not meet the scalability requirement or needs, relational databases still play an important role for those. And you can read it in the paper. One other point I should have added here in terms of major findings is that we don't always study the type of graphs that the users care about. We study graphs that a small group of users really pay attention to, but that happens. So one particular, as I said, graph type that I've started caring about and that I'll talk about today is what are called streaming graphs. This community is very familiar with streaming data, and so we basically streaming graphs combine the streaming aspects, which is unbounded data and usually high speed of data arrival, with the graph aspects, which is basically what is it that we're streaming, typically edges, and the graph emerges, you don't have access to the entire graph. And the use case that actually got me thinking about this was a number of years ago when I was having lunch with an engineer from Alibaba, and he quoted these statistics, and it took me a long time to really wrap my mind around both the size and the velocity of data arrival in these cases. So that really piqued my interest and started looking at this area. So there are real use cases for this type of processing, and I'll talk a little bit more about some of the issues. So the plan that I have is that I'm going to just go very, very fast on streaming data processing. I don't need to talk about this to this community, so I'll be zooming through a few slides just to make sure that we're on the same page. Then I'll introduce what I mean by stream graph processing, and then I'll end by about 15 minutes or so of the S-Graphito project that I and my 2 students are involved in. And the objective here is to highlight some of the problems that we're working on, but also use that as a segue to talk about some of the problems that are still open and that require attention. And then I'll conclude, and I'll be happy to take questions. By the way, most of my talks and keynotes as well have lots of citations, so I'll be happy to share the slides with the organizers so they can put it online. It's on my webpage anyway. So when you see citations, there's a talk that I won't show, but you can actually get the slides and find the references there. So let me start with the stream data processing first. So, the typical thing that we have, the inputs, which are one or more sources that continuously generate data in real time and in fixed order typically. And the fixed order we capture by timestamps, and these could come from a number of different sources. And the outputs is that we basically do operations on the incoming data and generate up-to-date answers continuously or periodically, depending on what our computation model is. And there are a whole chunk of applications. From a database perspective, the really important issue is that it represents a change in paradigm. Typically in databases, we are used to the idea that data is persistent and our queries are one-shot queries that are transient, and we get a query, ad hoc query, we answer it over the persistent data, and we produce a result. Of course, to materialize views and continuous queries over, or materialize view processing changes this a little bit, but this is the predominant model that we're used to. And in data stream systems, we're basically turning it on its head. It's the queries that are typically persistent. The persistent queries is what we work with, and the data is transient that flows through the system, and we're generating continuous results in one way or the other. So this actually changes. And there are additional differences of DSS that we all know, which that they're push-based. We focus on mostly persistent queries, although many systems allow at queries as well. And the unboundedness will actually come, and we cannot assume that the arrival rates are consistent. They might actually fluctuate. So there is a distinction between some of the older systems and some of the newer systems. So the older systems that I referred to are from the early 2000s to late 2000s that we all worked on. And these are really like Stream, Gigascope, Telegraph CQ, etc. And these are basically systems that attempted to provide the DBMS functionalities, a declarative query language, query processing, sometimes being able to query both streaming data and non-streaming data, static data at the same time, etc., etc. And these were, most of the work here was on single machine system, except Borealis, who looked at the distribution aspects. The newer systems that really started from about mid 2010s are almost all of them are scale out, and almost none of them try to provide DBMS functionality. So I'm thinking of Apache Storm, Spark Streaming, Flink, etc., etc. So these systems really do just are lower level processing systems, and don't try to provide database functionality. So this is probably an important distinction. Some of the characteristics that I've referred to in the previous slide as DSS are common to both, but some of them, but other characteristics are different between these two systems. So the typical system architecture that at least I will use is one where the data flows in. There is an input monitor, as we all know, that actually can do load shedding, etc., or just initial queuing. You might have some static data that you also access, but you also store whatever summary of the flowing data that you might want to do. You register your queries, so those are persistent queries, and as the data flows, the query processor will use both the incoming data and whatever you've stored in these summary to produce output. So this is the typical reference architecture that we kind of do, which doesn't really translate into anything that you can build in terms of a system, but allows me to talk about features of the system. So the typical data model, as we all know, is very simple. It's a timestamp and a payload. Payload could be many different things: relational tuples, revision tuples. In our case for this talk, the payload will be graph edges mostly, although you could have graph vertices as well, but I'll mostly focus on edges in the stock and other things. So that's really a simple model. This is what flows, sets of these or sequences of these is what flows through the system. So let me talk about how this model, when you combine it with graphs, what does it translate into? So we have this typical timeline, and we're at time t0, and nothing happens. At time t1, an edge comes, AB. At the top of this figure, I'm showing arrival of the edges. At the bottom, I'm going to be showing the emerging graph. So at time t2, nothing arrives, so the graph doesn't change. At time t3, nothing arrives. At time t4, the edge BC arrives, and I'm only looking at streaming edges here. So when BC arrives, then the graph emerges as such on the bottom. And T5, another two edges arrive, A to D and D to C. So the graph is updated, or the graph is growing. And T7, T9, and eventually you might have a explicit graph deletion in some systems, so you might lose an edge. And the graph is the fundamental point I'm trying to make here is that the graph emerges slowly or fast over time as the graph edges arrive to the system. So this really combines two really difficult problems. Streaming is difficult, we know, because it's unbounded, and it also graph processing has challenges because you're treating edges as first-class objects primarily, and that introduces significant challenges, and that is an issue. So the two problems that are important here are the unboundedness of the graph. So you never see the entire graph, which is really means that we need new techniques, because many of the techniques that we use assume that you have hold of the graph, and you can actually do things on the graph, and you don't here. And streaming rates can be very high in these cases. So the processing that you need to do could be very fast. So if you think about a reachability query, for example, where you basically say, show me all the edges, all the vertices that you can reach from A. At this point, it's only B. Now you can reach C. Now you can reach D. And so the query is persistent, and this is the edges are flowing through the system, so that you're producing results. That by the way is a relatively simple query to process. The graph computation models that people have that you can have on this case are two. One is the continuous processing, which is that you process as each edge comes. As we know from traditional stream processing, you can do this for only simple transactional operations. The more realistic queries cannot be done here, and this requires linear space, which is unrealistic if the graph is monotonically growing. Assuming you don't have any deletions, explicit deletions. You're not going to get there easily, and many graph problems are not solvable in this case. Theory community has worked on what they call semi-streaming model, which basically you can have sublinear space, and the assumption there is that you have storage to store the vertices but not the edges, and the thinking is that typically the number of vertices are much smaller than the number of edges. This is true in real graphs. So therefore, you can afford to store the graph structure in terms of the vertices, but have updates to the edges. If this is the case, I don't call this streaming. This is really what I call a dynamic graph model. You have the graph, and the processing algorithms have access to the entire graph, but there are updates to the graph. That's dynamic graph. That's not streaming graph. the fundamental property that differentiates for me streaming is unboundedness and continuous arrival. Okay. The other one is, of course, window processing. We use windows to batch edges, so that allows us that within that window, in this example of T5 to T10, you have a bunch of arrivals. So the graph is of a particular structure, and you can use that structure to process more complex queries. Sorry, I had to close my window. There is a vehicle outside. So that's the window execution. So to look at this, if the same example that I had, and if you were basically doing, again, vertices reachable from vertex A, and as time moves, and if you're doing continuous, you're basically producing edges as you go. So at T1, it's P, at T2 and T3, you don't produce any results. At T4, you get C. C is reachable from A through transitivity. So that's, you add C to the output, and you go. If you're doing window, there are certain points where, depending on what the window size is, where certain the edges, certain vertices will fall out of the results. So you have to manage the window as well as managing the generation of the output. And in the graphs, this is also true. You have to worry about this. Of course, you can have window processing and then insist that you have monotonicity in the query results. So you really, unless there are explicit results, you don't delete anything. It is just that the window moves and you move that way. But typically this is the case. Okay, so when we're talking about querying graph streams, and the title of the talk is streaming graph processing, meaning querying and analytics. So what do we talk about in those two areas? So when we talk about querying graph streams, what we're really talking about are two functionalities. One is subgraph matching, and I'll talk about these in subsequent slides. And the other one are path queries, typically reachability or shortest path and so on. So you're basically navigational queries are probably a better name for these. And you're trying, in the streaming case, you're trying to do this in streaming context, okay? And we're really talking about going beyond the simple transactional operators. So you're not just doing filtering, etc. One example in the types of graphs that we look at, which are kind of OLTP transaction graphs, is the vertices are users or customers or products, and edges might actually represent some interaction of the users with the product, purchasing or whatever. In another application, the edges might represent the events in the news. You're sending an alert to some set of users when an event occurs, event being represented as a vertex. So we're basically doing subgraph matching, and we're doing path queries. So that's, and I'll talk about these in the next part of the talk. There are some systems that have actually attacked this, and the word streaming appears sometimes in their titles, but these are really for dynamic graphs. They cannot deal with the unboundedness of the data graph. The other part of the processing is analytics, and there are many use cases: recommender systems, fraud detection, etc., where you're really doing analysis on the graphs, trying to determine certain patterns. And there are a number of existing works on this. Some follow the snapshot model, where they basically treat the graph as each change in the graph as a snapshot and do an entire processing on it. This is very hard to do if your arrival rates are very hard. The other one, the approach is basically says, why don't we take snapshots periodically and then do incremental in between? There are systems that have tried to do these, but they cannot, these are not designed to handle high velocity updates and hard to handle unbounded streams. So with that introduction, I'm going to talk about the S-Graphito project, which really, these observations in the last part caused us to start this project along with two students. As you can imagine, one student is looking at querying over streams. The other one is looking at analytics over streaming graphs. So I'm going to talk about in the remainder. What do I have? About 20 minutes. I'm going to talk about these two. And the objective is, of course, to highlight some of the things we're working, but in doing so, I want to highlight the type of problems that are still open in processing streaming graphs. So the S-Graphito project is basically looking at a HTAP type of environment, which is that we are looking at how we can handle both online, what are called online workloads, more OLTP, but workloads that actually are based on latency and throughput considerations, together with analytic queries on very high, graphs that grow very large and with high speed. So if you really consider that reference architecture, we not only have the querying part here, but we also have the analytics part as well. It is the same data that comes in, same input monitor, some commonality, but then you're actually have two separate streams perhaps over this data that you're doing. But there are certain things that will be common, with namely that window management and the fundamental stream processing techniques underneath are going to be common as you go through here. So that's the objective of the S-Graphito project. There are a couple of other things that we need to nail down. One is that we're working with what are called property graphs. These are different than, for example, RDF graphs. And the idea here is that each vertex and edge can have, in addition to the label that identifies the vertex or an edge, each of them can have additional attributes. In this case, for example, this is a part of an IMDb, which is about movies. So film 2014 is the label, kind of the identifier, and then you have key value pairs as attributes for these vertices. So these are the graphs that we assume in the S-Graphito project. The other thing is that we assume, by and large, that the arrivals are the payload that I talked about are streaming graph tuples. So we call those SGTs. So it's each of these is basically a SGT is an edge and a timestamp, event timestamp that's generated by the application. So when we actually talk about then windowing, our windows are basically these payloads, which are the edges and the operation on the edges. So this basically says in time tau1, we have edge AB, which is inserted, etc., etc., and there's a deletion in the end. And when we define a window, we define it as the open on the left, closed on the right interval, basically the set of SGTs that you come, or the records that actually come here. So each of these are records that are there, and that the window generates a snapshot of a graph, a streaming graph. And that's basically then when you're doing window processing, you're basically working on the snapshot. So these are the fundamental definitions that we use in the S-Graphito project for both segments and for both sides of this work. Okay, so let me talk about the what we do with the graph querying. This is the work of my PhD student Anil Pachaji. And this project focuses on a number of objectives. One is that we're trying to basically do persistent query processing over streaming graphs. So we're really not looking at ad hoc querying at all in this context. Our queries are registered and we're looking at it. And as I mentioned earlier, we're looking at two components. One is the path navigation queries, and for path navigation queries, because the streams are the graph is streaming, we're looking for non-blocking operators so that we don't have to do the processing we don't have to block the stream for processing, and we use regular path queries to model this part of the query model, and I'll talk more about how we do regular path query or RPQ processing in a minute. The other, of course, the navigation is sufficient. We want to extend it to a full query subsystem for persistent queries, and that actually means that we have to add graph patterns. So the graph pattern matching to the navigation which was the first objective, and this really one of the important issues here is being able to treat paths as first-class objects, and I'll talk about this here in a minute. But this is really not done very well, even in non-streaming graph query languages and systems right now. And finally, a lot of the work focuses on querying query structure, but these property graphs have attributes associated with vertices and edges, and we want to be able to process those. So let me talk about each of these, what we're trying to do and what we're doing or trying to do in each of these objectives. And that will highlight some of the really challenging issues that need to be tackled. There's a lot of room for more research here. So the design space for persistent RPQ, recursive path query algorithms, we characterize them in two dimensions. One of the dimensions is basically what is our path semantics. So when we talk about the path when we're investigating a path in the graph, what are we looking at? And this is actually the distinction along the two rows. So we have two type of semantics. One is simple, the other one is arbitrary. So in the simple path semantics, basically what you're doing is that, so the one on the left is my data graph, and I have this query which basically says, starting from a vertex, I want an edge which has a label follows, and then that needs to be followed by an edge which says mentions, and I want you to recurse over it. So I can take this Q1 and draw it as a graph. So I'm really trying to evaluate this particular graph over this graph, and that's basically how we do it. So the simple path semantics says that you're not supposed to be repeat a vertex. You're not supposed to be visiting a vertex again. So this is basically one solution. The thick lines is one solution. You start from X, follows mentions, and you find Y, and that's your answer. Okay. When you go to arbitrary path semantics, you remove that, and you basically say you can go visit the same vertex multiple times. It turns out that using simple path semantics is the query is very hard, computationally hard to do it. we can obtain efficient algorithms for certain subsets of these types of queries with simple path semantics. The second dimension of the design space for RPQ is the result semantics. So these are append only, or whether you allow explicit delete. Most of the work in even non-streaming graph queries assume append only. Append only is with fast insertions, and that's really easy to do. But allowing explicit deletes removes the monotonicity in your queries results, and that's actually more challenging. And what we've done in this work that we cite, which is appeared in this year's SIGMOD, is to really treat this entire design space uniformly and come up with algorithms for doing it. The other, when you go beyond path navigation, you really need to do combine subgraph matching with path navigation. So what I'm showing here is an example, is just basically the edge labels. So this is still a navigation query. And basically what we really want to do is, when we want to look at this type of structure and find in the data graph all the subqueries that have actually this particular structure. And that you can start with a subgraph matching. This is subgraph, you treat this as a subgraph matching, and then add path navigation to it by simply changing the label on one of these query graphs to a RPQ. So this will actually give you the combination that you're looking at. And we're basically, what we're really doing here is we're taking conjunctive queries and we're augmenting it with recursion over edges. Okay, so this is actually doable, and this gives you what is referred to as the unions of conjunctive RPQs, when this type of query is a UC-RPQ query, and this is quite commonly used in a bunch of these systems. Sparkle 1.1, the Cypher in some limited form, Oracle's PGQL use this. The problem here is that you really do not have algebraic closure. You do not you cannot have closure on this type of model, and if you don't have closure, you have difficulty in defining views and so on. So this is really not doable. So if you consider for example, this query, when you basically have this query that you did and this subquery that you have, and you want to recurse over it. So you're basically saying, I want to have that structure and I want to recurse multiple times of that structure, that you cannot specify in UC-RPQs, and that's a problem. So then you actually go to what are called regular queries, which is a subset of data log with algebraic closure. And these are computationally well behaved. And the thing is, the G-core query language is the basis. These type of queries form the basis of G-core, and this is what we're working with. And we're looking at an algebra for RQ and streaming graphs, and we're looking at a concrete implementation of this algebra. So as you can see, there's a lot of room for query models and implementation techniques here. I'll go very fast on doing paths as first-class citizens. We only looked in the queries that I showed you examples. We looked at the existence of a path. So is a vertex reachable from another vertex? So does a path exist? But we can actually increase this by putting a predicate on the vertex. So not only are you looking for this reachability, but you're basically saying that a path has to satisfy a particular predicate. This is when you have to actually treat paths as first-class citizens, and you need to be able to store and return and compare path, and you need to be able to do aggregation over paths and so on. So one approach is, of course, I can enumerate all the paths and then do a test on the path, the enumerated path, but this has very high complexity. The other thing that you can actually do is you can put structural restrictions on the path operations. The path has to be of at most a particular length, etc., etc., and these give you a handle on the types of queries that you can do. So we're working on data model and query languages that accept paths as first-class citizens and perform them on streaming graphs. So that's the other part of it. And again, this is wide open. And finally, the graphs with data. As I said, most of the real-world graphs have attributes attached to them, and you need to be able to query them. So this is, for example, a predicate on a path which is based on the data, not on the path structure, and we need to be able to process those, and that's a topic that we're working on as well. I had to speed up a little bit here, given that I'm running out of time. Oops, what happened? Okay, so somehow it moved too fast. So the second part of it is streaming graph analytics. I'll go through this at the same speed and highlight some of the issues. The objectives that we have here is, part of this is graph mining over streaming graphs. So basically trying to discover what the structure and the characteristics of these streaming graphs. So this is work that we're trying to do. The objective here are many things, and I'll talk about them a bit. The second objective of this line of work is really using representation learning over streaming graphs. So we're trying to really address the question, if you're given a stream of unbounded graph events, so SGTs, unbounded sequence of SGTs, and which have attributes attached to them, can you actually create embeddings for the vertices that capture both the data state and also the neighborhood in the graphs that are doing it? So, and finally, can you use these for a number of prediction-based analytics tasks, such as fraud detection and recommendation and so on? So the overall goal of this part of work is really to use machine learning techniques in graph analytics over streaming data. And of course, the challenging part of it is that these machine learning techniques typically require multiple passes over the data, and if the graph is streaming, you really don't have opportunity to do multiple passes, so you use windowing. This is the work of IDA, and this research is about 2 years behind the previous one. So I'll talk about what we're doing, but we don't have results yet. So when I talk about exploratory analysis of real-world streaming graphs, the idea here is that we're trying to determine graph patterns and look at graph patterns in these graphs. So one of the things is this conjecture that the rich get richer. So the idea here is what is the emergence pattern? So how do these patterns emerge over time? So as these edges come, and if you actually already have these graphs, so if this is the state of the graph at T7, and you have this edge that arrives, where does this edge attach in this graph? One assumption was that the rich get richer conjecture basically says it should attach to the vertex that has the highest degree. So if you look at this one, that actually probably means that it should be attaching to B, because B has 1, 2, 3 as the degree. But the investigations that I did showed that it really does not follow the rich get richer stuff. It could attach to somewhere else. So it attaches here, and then when you move on to the next time, that's the input, and you're looking at the other one. So this emergence pattern of the graphs is an important way, and the attachment rules and mathematically being able to model what these attachment rules are is what we're working on now. The other thing is looking at, really this is graph mining, looking at some of the patterns that emerge and to determine subgraph densification. So here, for example, one of the things that we looked at is detecting two biclics, or what are called butterflies. The green edges here are the butterflies, and how do these butterflies emerge? The counting these butterflies, similar to counting triangles in graphs, are important because they're the fundamental to determining graph cohesion, clustering, etc., etc. And how they emerge and how you can actually model this emergence is important. And one of the other issues is these are computationally very expensive to mine for these. And we've come up with a approximate mining framework, S-Graph, which where we can actually show that you get very close to actual counting, but it is more manageable. Another thing that we actually look at is connectivity. So if you have two subgraphs and they're going to be merging them, where do they merge? How do they actually merge, and so on? So this was a huge amount of study, both on on real graphs and synthetic graphs, to explain the results that we're getting at. So the question is, why are we doing all of this? One idea is that we're designing a streaming graph generator for use in our research. These are in short supply. Even real data is in short supply, but for scalability, you want to be able to do synthetic generator. And we wanted these generators to really mimic the patterns in the real graphs. So we did all of these studies. So the other thing that we're basically doing is, as I said, representation learning over streaming graphs. The idea here is the trade-off between effectiveness and efficiency. You can be efficient by actually reducing the size of your feature vectors over that you maintain, but you may not be as effective. And if you want to be effective, then you really increase the size, and then you have efficiency issues. So you have to deal with issues such as, again, unboundedness, structurally, how did these evolve, and the properties of data. And these feature vectors are going to be sparse. So how are you going to be dealing with that sparsity? How are you going to be modeling it? And a lot of the model-specific optimizations. If you're having heterogeneous graphs where vertices can represent different things, you're going to get heterogeneous embedding. You are going to have this graphical convolutions being dynamic, and having to deal with parameter training issues. Okay, so the idea here is you want to be able to deal with window semantics incrementally along with processing. And finally, the prediction-based analytics, and this is really where you're using this underlying structure that we study in the other one for specific applications that you're doing. And you basically deal with the case that you're managing a window while data arrives in one ingest window, while you're processing the other window for analytics tasks and so on. So I'll stop here since I'm going fast. So let me just do one thing. So I'll end by basically pointing out that these streaming graphs are real life and they occur in real applications. And I hope I've actually convinced you that these are really challenging. We're tackling a lot of problems that are not fully known in static graphs, and when you add the unboundedness of the streaming graphs and the high velocity, they become really challenging, both in querying and in particular in analytics, because of not being able to look. There are a number of publications, quite a number of publications in the community now with streaming in their title, but they're really not streaming. They're basically dealing with dynamic graphs. The updates are streaming, but the graph structure is available to the algorithms. And unboundedness in streams is real challenge, and you need to deal with that if you really want to deal with streaming graphs. And these are the entire field is pretty much open. It's I invite you to work on it, but it's challenging, so you may not get to write as many papers. With that, let me thank my two students, and we're collaborating with Angela Bonifati from the University of Lyon on it, on the first part of this, the S-Graphito project on querying, and a lot of my funders who fund this research. I'm happy to take questions. Sorry, I took about 4 minutes longer.
Thank you, Tamer, for that great keynote. We are now open for questions. And so please type your questions in the chat box, or if you would like to speak, please raise your hand, hopefully, and we'll catch you so that we can unmute you. I see a question here on the chat box from Bettina. You want to go ahead and unmute yourself?
Yes, hi. Great talk, Tamer. It was good seeing you again. I have actually two questions. The one, you had this at the beginning, and you just brought it again on your last slide, that streaming graphs is not the same as dynamic graphs. So I understand this from a conceptual point of view. What are the different applications? So when would you have an application that you would define that as definitely a streaming graph? And what is a typical application where you have maybe persistent queries in a dynamic graph?
Right. So for example, I'll go back to what the theory community calls semi-streaming systems. So if you have applications, let's take, for example, banks with fraud detection. In that case, you have a fixed number of clients. So if your clients if your vertices are clients, then your graph structure is fairly fixed. I mean, you might have updates, but the vertex updates, getting a new client, etc., is not a huge issue. The interactions that the clients might be having are the streaming edges. That is a dynamic graph. Okay, so because the graph might be very large, and you still have to deal with the scale, but you can build algorithms where you basically say that I have the entire graph structure in terms of the vertices that I can store, and I only actually do the updates to the edges, okay, whether updates. So that's dynamic. But if you don't have that closed ecosystem where you can actually fix your vertices change quite a bit as well. I mean, you can think about like eBay or Amazon or Alibaba or whatever. You know, they can control possibly the number of or they can batch the updates to the vertices which are which represent items in their catalog, but they're not going to be able to do that to their customers. The customers can actually sign on, so that will be streaming. So the other thing that I didn't mention is that it just came up. I should have. In the analytics part, we're really looking at, and that this is important more for the analytics than for the querying, for bipartite graphs. So we're looking at graphs where the vertices are, the edges are between two different types of vertices. So exactly the customer and an item, for example.
Well, then would be one part would be more fixed and the other part could be, you could have only for
It-
one part,
it
your
could be.
nodes could be
could be.
UNIOD. Okay,
Yeah.
very
Yeah,
interesting.
as a driving application, we're looking at those types of things in that part of the research.
But I think it's a little bit fluid of where you would say.
It is fluid. I think the fundamental issue for me is, or at least the way that I mean, this actually comes up in even streaming data, regular streaming data, right? What is the difference between streaming data and dynamically changing, dynamic updates to a database? Yeah. And I think the at least mentally, my mental model is that one has to deal with the issue of unboundedness. Okay. Going back to very early 2000 to 2003, or maybe 2004 pods Keynote, that actually proved that a lot of these streaming problems are not doable unless you have infinite memory. Okay. So the fundamental criteria there was unboundedness.
So very good, and you bring here to my second question by mentioning pods. You know, when I go my first undergraduate class, it's an algorithm class. I hear about algorithms, and most common you learn a lot of mechanisms around algorithms. So there's a whole different community to ours that looks at graphs.
Yeah.
How similar is that research? Do you collaborate? Are there any insights? Is there overlap? Do our problems, you say a lot of, these problems are really hard. And so could we benefit from reaching out to that community and taking the experience, or give them the really more theoretical problems?
I certainly think so. And I think we don't necessarily collaborate, but we follow, because some of the research in that community actually tells you what is doable, what is not doable. So you can actually look at how you can structure the more algorithmic aspects of your work based on the theoretical results that they're giving you. So we certainly follow. I don't know that we actually do any research that's publishable in that community, but we try to keep track.
We should give them teasers to say, look, here's a nice problem. Can you solve it?
Yeah.
You know, can you inspire your research community? And then they come up with variations that we haven't thought about.
Yeah.
Right. Any other questions? Okay. Kaiwen has a question. Go ahead, Kaiwen.
Hi, Tamer. Thank you for the talk. It was very interesting, and yeah, I really enjoyed it, because we're trying to study something similar as well. So actually with Bettina. So with regards to RPQs, right, regular path queries. So I was wondering if you also, because I know you mentioned publish subscribe somewhere in your talk, and of course that's a very relevant topic for us here at DEBS. So I was wondering if there's any concern with disseminating those query results as well to a large number of subscribers, as you would do in the publish subscribe system. So just a question concerning the dissemination aspect other than the evaluation aspect.
Yeah.
Thank you.
I think that is actually a valid part of it. It's not part of our research. I think we stop when we can actually find algorithms to continuously generate results of it, and how those results get disseminated in an efficient manner to quote unquote subscribers is not something that we look at in this project. So our work is far more on the data management side than on the publish subscribe side.
Okay, I see. So what do you do if there's like multiple queries that are the same or similar? Yeah.
I think it is on our plans. Whether Anil will get to that or not is, I'm assuming Anil wants to graduate at a reasonable time. So there are a couple of things that are on our radar screen. I think with persistent queries, of course, multi-query optimization is a huge opportunity. So that is on our radar screen. We talked about it. The other, of course, is that for both the analytics and the and the querying part for both Anil and Ida, if we really want to reach high velocities, or be able to handle high velocity streams, we will need to look at scale out solutions to many of the things that we're doing. So that's on our radar screen. But yeah, I would doubt very much whether either Anil or Ida will get into those if they want to graduate in a reasonable time. So it might be the next student or collaboration.
Are you aware if there's a lot of related work in that aspect, like multi-query optimization in graphs, or? I think
not that I know of much, but
I see.
I think Anil was going to be on the call. So Anil, if you know, then type in the chat box or on the Slack channel. he might know.
Yes, I do see Anil.
So there is a question from somebody in the audience in the chat box, and I'll read the question to you, Tamer.
Okay.
Streaming SQL framework use generic and extensible libraries to optimize the logical and physical plans of a query. Catalyst for Spark and Apache Calcite for Flink. Do you think this kind of library can be used for optimizing and creating physical plans for queries?
Right. Good question. Actually, some library is useful, and whether it's Flink or whether it's Calcite or Catalyst or something, but some type of library will emerge. In other words, eventually, let me just focus simply on the RPQ side, because that's where we did a lot of work. I introduced RPQ as a physical operator that for non-blocking operator for doing some of the querying. So now there comes the issue of how do we implement RPQ? You need something underneath that actually either you build it from scratch, or you need something underneath for basically managing the streaming and the graph evolution aspect of it. So whether you build it on top of Flink, or whether you build it, in our case, at least our initial try that Anil is doing is using Timely, because Timely actually Timely data flow handles it easily. Something of that type is reasonable, and then you will actually develop a set of libraries that will actually do additional value-added work for you on top of those basic execution platforms.
All right. Okay. Any other questions? I think we are also slowly approaching the next session, which is a research session, but it looks like, okay.
All right.
All right. Well, thank you for this great keynote, Tamer. Can you just stop sharing your screen, please?
I thought I did. It told me that I wasn't sharing it anymore.
Oh, okay.
So I think we're fine. You can take control of the screen.
All right.
All right. Thank you for the invitation, and thank you everyone.
Okay, just a second, Tamer.
For listening.
Let me see if I can do this. I'm going to try to share my screen again in the hope that I can do this.
You should be able to, because it told me that I.
Okay, there we go.
Yeah.
On behalf of the DEBS organizers, thank you so much for taking the time, to give a great keynote. This is virtually for now, on its way in actuality. So please have one for us.
Wow. And it's an 8.
Thank you,
Column 18. Thank you very much, guys. Thanks again for the invitation.
Thank you.
Thanks.
Bye-bye.
Thank you, Tamer.
Okay, please, join in applause and thank Tamer for the great keynote.